Hello, everyone. I hope you're all doing well today. Today, I'm going to talk to you guys about quarks and other subatomic particles. To begin with, what are the different subatomic particles? Subatomic particles in the Standard Model are divided into two families. These families are fermions and bosons. Fermions are mass particles, and bosons are energy-carrying particles. The fermions, there are 12 different fermions, which are divided into 6 quarks and 6 leptons. The fermions are mass particles, and each of the 6 quarks in the fermion family have a flavor and charge property. The leptons include the electron, muon, and tau, and their respective neutrinos. So, what are the uses of these subatomic particles? So, if you look at quarks, for example, there are 6 different types of quarks, and these 6 types can be rearranged into different models and then bound with gluons to create new particles. For example, a proton will have two up particles, two up quarks, and one down quark. Each up quark, each positive quark, has a two-thirds electrical charge, and each negative quark has a one-third negative electrical charge. So this adds up to give the proton its positive one electrical charge. The opposite happens with electrons. Fermions make up all of matter, and various fermions can be arranged into protons, neutrons, and other particles. Bosons are energy-carrying particles, including the photon, which represents electromagnetism, gluon, the strong nuclear force, and W and Z bosons, which are the weak nuclear force. These particles each represent one of the four forces of the universe, with the only exception being gravity. Gravity is an outlier and does not fit into the Standard Model, and is instead described by general relativity. One of the biggest questions in physics right now is how to integrate relativity with the other parts of the Standard Model. So, what are some possibilities for the Standard Model and other subatomic particles? Scientists are trying to discover the graviton currently. The graviton would be the gravitational equivalent of the other particles in their Standard Model. If the graviton were to be discovered, we could merge it with the rest of the Standard Model and, in theory, have one equation almost fully describing the universe. This equation would in turn lead to more advanced fields of research, such as string theory and supersymmetry. The discovery of a graviton would also entail the discovery of its antiparticle, the antigraviton. This particle could, in theory, fuel anti-gravitic technologies, something only limited to sci-fi right now. The discovery of other particles also expand the Standard Model, and by extension our own knowledge of the universe. One of the most recent particles to be discovered was the Higgs boson, which I created a video about, which you guys should go check out. The reason that the research into these particles is important is because the more we get to know about these particles, the more we'll know about the universe itself, and by extension, more new technologies and new theories that we could come up with. I hope you enjoyed this video. If you did, please make sure to like and subscribe to my channel, and I'll see you next time. Bye.